So what we're looking for now is a visualization that clearly shows that when we increase our sample size, the more in line our sample statistics are with the corresponding population statistics, or the more accurate our approximation becomes. Now we can do this because we generate our own data. We generated our own population distribution, and thus we have access to the actual population statistics to which we can compare. So what we're going to do is we're going to take samples from the same population, but just with an increasing population size. And each time, for each sample, we compute the sample statistic, the mean and the variance, and then at the end, we will collect all of these sample statistics and see how they evolve towards the population statistics if we increase the sample size. Now this will make more sense when we go into the code and see how this is done. In the first line of code, we define an array that contains all of the sample sizes that we want to look at. We can do so by typing numpy.arrange, a starting value of 5, so the lowest sample size that we will look at is a sample with 5 data points, and an upper limit of 20,000. So our largest sample size will be 20,000 data points. And this third parameter is the increments in which we will increase our sample size. So concretely, in this case, we will get 50, 55, 105, 155, and so on, all the way to a sample size of 20,000. So these are all of the sample sizes that we will look at. The next step is to define upfront the lists in which we will collect the sample statistics. One list for the sample means and one list for the sample variances. And then we come to the part of the code where all the magic happens, basically one single for loop. So we are going to loop over the different sample sizes. And for each sample size in our array of sample sizes, we define n sample, which will be this specific sample size. Then we draw a sample with this specific sample size from our population, and we will choose pop1 to be our underlying population. We do this by defining sample1, which will be a Python array, which is equal to numpy.random.choice, which we're already familiar with now. We choose from our population 1, and the size will be our n sample. Then, once we have our sample with the specific sample size for this step in the for loop, we can compute the sample statistics. So we do sample1.mean to get the average of this sample, and we can get sample1.var to get the variance of our sample. And then we can store these values into the lists that we defined earlier. We start out with an empty list, but at each step in our for loop, we append this new sample statistic. Then once we've gone through all of these sample sizes, so once this for loop is complete, we still convert the lists that we made that collected these sample statistics into Python arrays so that we can plot them more easily. And then we come to the plotting part of this cell. And this will be a simple line plot. So we again define our figure and axis, and we will again have 4 plots, 2 by 2. In the first panel, we plot on the x-axis the sample sizes, because that's how we see them evolve. And on the y-axis, we will plot the sample means. This means that for each sample size on the x-axis, we have a corresponding value for the corresponding mean of that specific sample. And then we want to compare this mean for each sample size with the corresponding population mean. And to do this, we plot the population mean as a horizontal line. In this case, we will plot it in the color red and as a dashed line style. And we will give it the label population mean. Then we set the title, the X label, the Y label, and we plot the legend. Now we can do exactly the same thing for our variance. Instead of taking the sample means and plotting them against the sample sizes on the x-axis, we take the sample variances and plot them against the sample sizes. So this is exactly identical. Now what we can also do is, instead of looking at the actual values of the sample means and the population means, we can look at the difference between, on the one hand, the population mean, and on the other hand, the sample mean. And we expect that if we increase the sample size, this difference will go to 0. And that's exactly what we can do in these plots. Here we again have a line plot where again on the x-axis we have the sample sizes, and on the y-axis we take the difference between the population mean and the sample mean. However, because the sample mean sometimes is above the population mean and sometimes it's below, it fluctuates between these two, we can take the average so that we might get this nice smooth curve going to 0. And we can do the exact same thing for the variance. We compute the difference between the population variance and the sample variances. We take the absolute values and we compare them with the sample sizes on the x-axis. Now, if we run this cell, we get the following plots. On the x-axis, we see the sample sizes going from a little bit above 0, so 5 was our smallest sample size, all the way to 20,000, each time in increments of 50. Now we see that the dashed red line will be the population statistic. For the mean, it will be 1, and for the variance, it will be 0.25. Now, what we can observe from these graphs is very interesting, and it shows the beauty of simulation. We see that for low sample sizes, on the left-hand side of these graphs, that there is a lot of fluctuation around this population statistic. Sometimes it's above the population statistic, and sometimes it's below. And for smaller sample sizes, these fluctuations are very large, meaning that the approximation might be very off from our actual population statistic. And we see indeed that if we increase the sample size, for instance in our mean, that these fluctuations, they dampen down. And if we keep on increasing them, the values of our sample statistics will more likely approximate and converge towards the population statistic. Now these right panels, they show exactly the same dynamic, but now by looking at the difference between the sample statistic and the population statistic. And we see that this should indeed go to 0. And indeed also here is the case that for smaller sample sizes, we have larger fluctuations, and for large sample sizes, these fluctuations tend to go to 0 and we approach our population value. Now, as before, you can play around with the values. For instance, you can get to even larger sample sizes, or you can go with lower sample sizes. Again, you can play around with this and see how these plots change. And this concludes chapter 3, where we learned about generating data and all of the benefits that comes with it. In a sense, it laid the foundation for both concepts and code for all of these subsequent chapters, where we will learn about more complex and abstract statistical concepts. And the next chapter will be a very fine example of this. We will use our simulation tools to get a more intuitive approach to the central limit theorem, a central theorem in the entirety of statistics. So I will see you in the next chapter.